So the objective over here is to cover a large spectrum of topics related to vector embeddings and vector search, and provide as many pointers as possible for listeners to explore each topic further. But we'll not be going into a lot of depth in each of these topics, given the time constraints. Okay, but I'll try to cover a large spectrum of topics. So here is the structure. We'll start off with introducing what vector embeddings are, then we'll see where they are applied, and then we'll focus on how to generate vector embeddings for text data, and finally we'll touch upon what is vector search, what are the various approaches for vector search, what are the algorithms and libraries. Okay. Someone has typed in the chat. Okay. Yeah, so here are the common data types that we can see over the internet. That is text, images, audio, and video. We'll also have numeric data on the internet, but majority of the data we'll see is in the form of text, images, audio, and video. As we know, like computers are programmed to, are designed to operate on numeric data. We can store text, images, audio, and video on the disk and visualize them. But in order for us to perform useful, powerful operations on these kind of data sets, we have to convert them into numeric form. Okay, when I say numeric form, we are talking about vectors or embeddings. So we have to find a way to convert text or images or audio or video into numeric form or vectors, so that more meaningful operations, powerful operations can be performed on that kind of data. When I say meaningful operations, I mean search or inference or something like that. So how do we convert the raw unstructured data into meaningful numeric vectors? So usually we use AI models for that. There are specialized AI models or deep learning models which convert text data into vectors. There are specialized AI models which convert images into vectors. Similarly, there are specialized AI models which convert audio into vectors. Okay. Here, the significance of this AI model is that it has to capture the context or meaning that's present in the raw data. If it is unable to capture the context or meaning that is there in the raw data, then the vector it produces is going to be basically useless. Okay. So the significance of these deep learning models is that they are capable of capturing the contextual meaning in the data. And these vectors which encapsulate the context or the meaning in the data, those vectors are called embeddings. Okay. Otherwise, we can generate vectors randomly as well, but not every vector is an embedding. Embedding are those vectors which encapsulate some amount of knowledge or meaning that's present in the raw data into them. Okay, so this is the beginning of it. Now that we know how to convert the raw data into vectors, what can we do with these vectors? How do we compare vectors? How do we find similar vectors? What kind of measures can we use? So there are three popular measures which can be applied to compare vectors. These are Euclidean distance, dot product or inner product, and cosine similarity. Cosine is a trigonometric cost function that we have studied in our school days. Okay, so these are the three standard approaches to compare vectors. But which of these three should I use? Okay, that's an important question. And what decides which of these three we have to use is the choice of AI model that we make. Okay, some AI models are optimized to generate vectors which can be used to compare with the cosine similarity. Some AI models are optimized for inner products and some are optimized for Euclidean distance. There are some models which generate vectors which can be compared with all the three metrics. Okay, so one thing we have to note down is what kind of AI model we are using. We have to make sure that we have to use a metric that matches with that AI model. Second thing is, okay, suppose we have a model which can be applied, which can generate vectors which are compatible with all the three metrics. Then what can we do? In that case, we have to again look at the data sets, try to do some experimental analysis and see which kind of metrics works best for that particular data set. For example, if you talk about a recommender system, recommender systems usually use like dot products. The data that they have works very well with dot products. Similarly, some text data sets work very well with cosine and some with inner product. Okay, so the metric that we have to choose is important, and the choice depends on the kind of AI model that we are using and also on the data sets. Okay, so let's look at the geometrical way of interpreting these metrics. So here you have 4 graphs in the screen, and you have 2 vectors A and B. So in the leftmost graph, you see the angle between the 2 vectors is 0. Basically, they are aligned in the same direction, although they are of different lengths. In the second graph, you are seeing that the vectors are at 90 degrees angle. In the third, you will see that the angle is 180 degrees. And in the fourth, the angle is still 180 degrees, but the length of the vector B has been shrunk down. So how do these metrics behave when we change the angle and the length of these vectors? Cosine of the cosine similarity is nothing but the cos of the angle. So when angle is 0, the cosine value is 1. When angle is 90, the cosine value is 0. When the angle is 180, the cosine value is -1. When the magnitude has changed, angle has remained the same, the cosine value will not change. So cosine is purely dependent on the angle. Okay, but the other two metrics rely both on the angle as well as the magnitude. So the dot product is positive when the angle is between in the range -90 to +90, and beyond that the dot product is a negative value. When the vectors, the magnitude of the vectors or the length of the vectors, when it increases, obviously the dot product increases. And when the vectors shrink in their length, the dot product, the absolute value of the dot product shrinks. Okay, sign depends on the angle, and the absolute value depends on the length of the vector. And the Euclidean distance is the distance between the tip of one vector to the tip of the other vector. As you can see, as the direction changes, the Euclidean distance also changes. Okay, and if the magnitude or the length of the vectors shrink, the Euclidean distance obviously shrinks. Okay, so there is one more thing important over here is the cosine similarity takes values in the range -1 to +1. Dot product takes values in the range -infinity to +infinity. And Euclidean distance is always positive, so it takes values in the range 0 to infinity. Okay, these are the 3 most commonly used metrics. And next, we'll see where these vector embeddings are used and how they are used. And we'll cover only the common applications. Of course, there are many more applications beyond this, but we'll see some of the most common applications of vector embeddings. The most popular is text search. Text search relies heavily on vector embeddings. So here in this Bing search, I have given 2 keywords, Sachin and divorce. If I had given only Sachin, then obviously the first reply would have been Sachin Tendulkar. But I have added a context, another context word to it, which is divorce. So the result has changed to Sachin, instead of Sachin Tendulkar, to Sachin Pilot. Okay. So here, text search, what it does is you give as everyone has used it, you give the query, it returns you the most relevant documents based on the keywords. Now coming to question answering, here I have changed the context word slightly. Instead of giving the words, I have added another context word called "Who is Sachin's coach?" Okay, and the response is something else. Here the system, the question answering system understood that, okay, here we are talking about Sachin Tendulkar. So the answer is Sachin's coach was Ramakant Achrekar. So the main difference here between the two searches is, one thing is the context has changed. The other thing is that in the simple text search, you get the most relevant documents, whereas in the question answering system, the question answering system actually generates the right answer for you. Okay, so here you can see Sachin's coach was Ramakant Achrekar, etc., etc. This answer is generated by the system. Okay, so first it has to understand what the user is talking about and then get the relevant information and then generate the answer. All of these systems rely heavily on vector embeddings. Here behind the scene, all the knowledge, all the text is embedded in the form of vectors, which is stored in vector databases or vector search engines. When the user submits a query, there is a call to that vector search engine and the results are fetched and shown. Similarly, image search. This screenshot is taken from Google's advanced image search. Here, the query is not text. Rather, the query is this image on the left-hand side, which is the wax statue of Sachin Tendulkar. Okay, so the task for the image search is to find all the images which are similar to this. So here in the second row, it has found out all the links where it has found this image. Okay, and not just that, it has also identified that this is Sachin Tendulkar, and it has returned images, other images of Sachin Tendulkar, not just the wax statue image, but normal images of Sachin Tendulkar. So this also relies on vector embeddings. Behind the scene, all the images would have been stored in the form of vectors in a vector database. And when a query goes, it goes to that vector database and results are retrieved. Okay, similarly, a recommender system. All of you might have used some kind of e-commerce site or some OTT platform where e-commerce site recommends their products and OTT platform recommends movies or TV series. Okay. Here also, when they are making recommendations, the way they store the data is they transform the product information or the movie information into a form of vector. They do not use AI models to do that. They use something called as matrix factorization or collaborating filtering to achieve it. But still, they store the information corresponding to their products, be it e-commerce product or be it movies, in the form of vectors. And all those vectors are stored in a vector database. And when they want to make a recommendation to an individual, they look at that individual's search history, what kind of movies they have watched, or what kind of products they have purchased, or what kind of products they have seen on the website. And they try to find similar products from their database. So the word similar, right, this will occur over and over in this talk, because essentially what we are trying to do is do a similarity search. Okay, so the kind of products the person has purchased in the past, or the kind of movies he has watched in the past, similar kind of products or similar kind of movies are fetched from the database and recommended to the user. This is a new research, molecular similarity search. So what they did over here is it got published in 2021. So here they have tried to build a database, vector database for DNA. Okay, so DNA is typically represented as a string, as a large sequence of string. And as part of this work, they have converted that string into a vector using an AI model. It's a vision model, computational neural network. They have applied that to convert the DNA string into a vector, and they have stored the DNA information of various entities into their vector database. Now, the useful thing about this is whenever they want to compare, find DNAs which are similar to a particular DNA, the search happens very fast for them. Okay, so this is yet another use case. So all of these use cases behind the scene, they rely on vector embeddings. Vector embeddings act like a knowledge base for all these applications. And here is the big picture. Almost all the applications fit very well into this big picture. Okay, where you have lot of unstructured data. The data could be text, it could be images, it could be audio, it could be like DNA sequences. Okay, a lot of unstructured data. The first thing you do is pick an AI model which suits for your data, okay, which is compatible with your data. Okay, and that using that AI model, you convert all your unstructured data into vectors. Once you have converted all that data into vector form, you select a vector search engine, dump all the data into that vector search engine. Finally, this vector database acts like the knowledge base for that particular application. You can build many applications on top of it. For example, if you want to do a text search, when a user enters a query on the text search app, the text search app makes use of the same AI model that was used to convert text into vectors. Okay, so here we take the query that was entered by the user, we send that text query into the same AI model, and as a result we get a vector. This is the query vector. So when we call vector database, instead of sending the text, we send the query vector to the vector database, and we ask the vector database to fetch vectors which are similar to the query vector. Okay, and then we want to do it efficiently also. Okay, so this is the big picture. Okay, so you have a lot of unstructured data, dump it into AI model, get the vectors, take the vectors, dump them into the vector database, and now build the apps which interact with the vector database. Of course, the apps will also use the same AI model to convert the queries into the vector form. Okay, so this is the big picture, and now we will look into how can we convert text into vectors. Okay, if you are interested in images, there are other AI models. Just for your reference, you can look at ResNet, Inception, VGGNet. There are many other models nowadays. Even vision transformers are coming up. So there are specialized models for images. There are specialized models for audio. For the sake of this discussion, we'll stick to the text part of it. Okay. So this is the key paper over here. Sentence BERT, sentence embeddings using Siamese BERT networks. So BERT is a very popular language model. It's a deep learning model. It is a transformer model. Basically, transformers were developed by Google and somewhere around 2016-17. And a year later, BERT was also developed by Google. So BERT is a language model, and we can use BERT to perform many NLP tasks. And in this paper, the authors have used BERT to build something called as a Siamese BERT network. This is also a deep learning model, which is specialized to encapsulate or extract the meaning from the sentence, the meaning from text, and convert it into a vector. Okay, these are trained in a very specialized way to extract information from text and convert them into vectors. And there is this open source library, sentence transformers, which is based on Python, PyTorch, and transformers framework. So this library supports up to 100 different languages. You can, if you have text in 100 different languages, you can convert that into vectors. And also this library has a lot of pre-trained models. So you don't have to train anything from scratch. And there are a lot of pre-trained models which are already available for you. Here is the link on the website. You can go there and take a look at all the models that are available. The models are in different sizes and shapes. So here is the smallest model, which is 43 MB in size, and here is the largest model, which is 970 MB in size. Almost all of these models are derived from SentenceBird. They are extended from SentenceBird. Okay. What is different when compared to the original paper is the kind of data on which they have trained, and also not just the data, but in some cases the training algorithms are also specialized, are also extended basically. So here is the very popular MPNet based 2 model, which was trained by Microsoft. This is also freely available on this website. So here they have modified the training algorithm as well. Not just although they have trained it on a lot more data, on 1 billion training data points, but also they have modified the training algorithm as such. And this model generates a vector which is 768 dimensions. Okay. Usually this is another factor. The accuracy of the model also depends on like the dimensionality of the model. Some of the smaller models generate vectors which are lesser in dimensions, lesser in size, but they'll have different accuracies, different performances. Okay. So this model generates a 768 dimensional vector. It is of 420 MB size. And now, as I was talking earlier, what kind of measure or metric, similarity measure we can use when we are using this model? We can use dot product, cosine similarity, and Euclidean distance. So this is compatible with all the three. Okay. And here is a simple code snippet. It's very straightforward. All one has to do is, after installing the library, load a sentence transformer object by specifying the name of the model. The name of the models, all the names of the models are available on this website, and also the descriptions of the models, on which data set they were trained and how they were trained. If you, for example, if you open this link over here at the bottom, you'll see the reference to the paper which describes how MPNet was trained. Okay, so all those descriptions are available. All you have to do is load this particular model and create a list which contains all the sentences that you want to get converted into vectors. Pass that list of sentences to the model's encode method, and you'll get back the embedding. So in this particular case, we have passed 3 sentences to the encode method, and it will return 3 vectors. Okay, so this is as simple as that. But let me tell you that this is not the only way of converting text into sentences. There are many other techniques. For example, if you look at OpenAI, they also like give you APIs. You can pass the text and get back embeddings from them. So there are many other sources of converting sentences into vectors. But by far, SentenceBird and its variants are the most popular ones. So now that we have seen how to convert text into an AI model, the next thing is about deciding what kind of vector database to choose to dump all these vectors into the database and what approach to choose. Okay, so remember the main goal of this vector database is it is given when a call, API call comes to the vector database, it is given a query vector. And the vector database has to do a similarity search and find vectors in the database which are very similar to the query vector. When we say very similar, we are talking in terms of similarity metrics. So the similarity metric will be decided ahead in advance. When you build the database, you have to choose what kind of metric you want to use to build the index. Okay, and one of the metrics will be used, not all the three. When you are building a vector database index, you'll use one of the metrics, and based on that metric, a similarity search has to happen. Okay, and it has to happen efficiently. That is an important thing in practical applications. So how do we measure the efficiency of a vector database? We can measure the efficiency in terms of data volume. How much volume can the database ingest? Okay. Search latency is another metric. How fast it is in giving the search results. Then the second thing is search accuracy. How accurate it is. Okay, so the accuracy over here is measured in terms of a metric called recall. So when we give a query vector, and let's say we ask it to return 100 similar vectors. So the vector database returns 100 vectors. Of the 100 vectors it has returned, maybe only 90 of them are the nearest to the query point. 10 of them are somewhat far off vectors, not the near ones. Okay. Then we say the recall is 90%. Okay. 90 of them are nearest, but the 10 are not nearest. So out of 100, 90 were the right ones. So the recall is 90%. Okay. Infrastructure. So as you'll see in few slides from now, different algorithms, different techniques of building vector databases require have different requirements in terms of memory, in terms of computation, CPU, GPU, etc. And eventually all this will have an impact on the cost. Okay. So all these metrics are important to while we are evaluating or while we are selecting a vector database. Okay, before we get into the specifics of algorithms, I want to mention that vector search can be broadly classified into two types. One is exact search, which is deterministic in nature. The other is approximate nearest neighbor search, okay, which is somewhat probabilistic in nature. So in exact search, what we are saying is we want a recall of 100%. Okay, if we send a query and we ask the database to return 100 nearest vectors, then the database has to return 100 nearest vectors. That's it. It cannot return 90 nearest vectors and 10 somewhat far off vectors. So to do this, there is no other way, at least as of now, but to do it in brute force. Okay, one has to compare the query vector with all the vectors in the database, and that is computationally intensive. Okay, but if the application demands exact search, maybe it is some very stringent requirement in the application that it has to have a very high recall, then exact search is unavoidable. But a lot of the applications, for example, like internet text search, question answering, all of them, you'll see that 100% recall is not the such a high requirement. All we need is like a good 95, 98% recall. Search engines can absorb some amount of uh, bad results. That's okay. At the end, user can filter it out. Okay, so that is where uh, comes the approximate nearest neighbors algorithms, which exploit this aspect that you don't have to return exactly all the correct results. You can take some hits. Okay, and if you are taking a hit and recall, you can improve your speed, you can improve your cost, and all the other things. Okay, so here, so approximate nearest neighbor search, the algorithms come in various flavors. Okay, various. I mean, there is a very large list, but the most common ones. Again, these are not individual. The clustering based is not an individual algorithm. There are many clustering based algorithms. There are many tree based algorithms. There are many graph based algorithms. So I have broadly classified the approximate nearest neighbor algorithms into clustering based algorithms, tree based, graph based, and some are hashing based. And there are some algorithms which are like hybrids. Okay, they combine multiple approaches in order to, achieve, improve the efficiency. So let's get started. The first approach is clustering based approach. Okay, so first of all, what is clustering? So we can imagine vectors as points in n-dimensional space. So if the vector is two-dimensional, that means it has just two values in it. So it will be a point in two-dimensional space. If it has three values, it will be a point in three-dimensional space. If it has 768 values, it will be a point in 768 dimensional space. Although we cannot visualize it, higher dimensional space, but nevertheless, these are all points in higher dimensional spaces. So when these are points in higher dimensional spaces, what clustering does is clustering groups points which are close to each other into what is called as clusters. Okay, so here is a two-dimensional representation of that. So in this graph, in this plot, you can see that all the color-coded regions, right? Each of them constitutes one cluster. So all the points in the blue region correspond to one cluster. All the points in the red region correspond to one cluster, like that. So there are 10 different color-coded regions. So there are 10 different clusters. So every cluster has a centroid. Centroid means if you take the average of all the vectors in that particular cluster, that average becomes the centroid of the cluster. It's like the center of gravity of that space. Okay. So this is what is meant by clustering. How do we achieve clustering? It's a 60, 70 year long literature. There are just too many algorithms, hierarchical clustering, DB scan, spectral clustering, so on, so on, so on. But as the volume of the data increases, the amount of time taken to do clustering will also increase. So the algorithm which can cluster data, large volumes of data quickly, is an algorithm called k-means clustering algorithm. Okay, k-means clustering algorithm. In almost everywhere, wherever we use clustering for doing nearest neighbor search, mostly we are going to rely on the k-means clustering algorithm. All the algorithms at the end, they achieve the same result. K-means also achieve the same result. How they achieve is in different ways. Okay. Nevertheless, so let's say we have used some algorithm, some K-means algorithm to cluster our data, and finally our data is clustered, like we are seeing in this pictorial representation. Okay, so we have 10 clusters, and every cluster has some points in it. Okay, and every cluster has a centroid point also. So how can we use these clusters to improve our nearest neighbor search? So if we are doing an exact search, what we will do is we'll take the query vector and compute the distance between the query vector and all the points in this database. All the points. Okay, that is the brute force approach. That is the exact approach of doing things. But if you want to do it approximately using clustering, what you can do is you can first compute the distance between the query vector and the centroid vectors. Okay, so there are 10 centroid vectors. So compute the distance between the query vector and all the centroid vectors. So you will get 10 distance values. Pick those centroids which are closest to the query vector. How many such centroids should we put? That is a hyperparameter. Okay, it can be decided later on. Okay, so let's say for the time being, we say that okay, we will pick 3 centroids which are closest to the query vector. Okay, so let's say we have picked these 3 centroids over here at the bottom. So once we have picked these 3 centroids, what we'll do is we'll take only the points belonging to the clusters of these 3 centroids. Okay, and then compute the distance between the query vector and all the points in these 3 clusters only. Okay, so there are 10 clusters. Out of the 10 clusters, we are computing the distance between the query vector and the points in just 3 in these 3 clusters. So approximately we have reduced 70% of the effort. Okay, if we have reduced 70% of the effort, what is the trade-off? The trade-off is that we lose some amount of accuracy, some amount of recall. Okay, so if we have to improve the recall, we have to not just look in 3 clusters, maybe we have to look in 4 clusters or 5 clusters. So as we start looking into more and more clusters, we'll see that the recall improves, but the amount of computation that we have to do, that also increases. If the computation increases, the latency also increases. Okay, so there is a clear-cut trade-off over here. If you want to improve the recall, do more computation, and which will increase your latency. But the good thing about this is that this supports parallel computation. So if you have a server which has many cores, then this technique is good in the sense that it allows you to do a lot of parallel computation. Also, if you have GPU support, then this technique is still even good in that scenario also. Okay. So this is the first and the most simplest approach of using clustering. The second approach is based on the tree data structure. Okay, this algorithm is called Annoy. So what it does is it builds a random binary tree. Okay, if you all recall, a binary tree is a tree in which every node has 1 or 2. Every node has actually 2 children. Okay, so here the way they construct the tree is you start with the root node. A root node resembles all your entire data set, meaning it contains all the data points in the data set. Now the way you have to create a subnodes of the root node is by finding a random hyperplane which cuts the space into two halves. Okay. How do we find this random hyperplane? Is by randomly selecting 2 points. Let's say we have selected this point and this point. Okay. So if we have selected these 2 points, then we'll draw a hyperplane which is actually orthogonal to the line joining these 2 points. At the same time, it passes through the center of these 2 points. Okay. So we have selected these 2 points randomly, and then we have drawn a hyperplane which passes through the center of this line and which is orthogonal to this line. Okay. So this is a random way of splitting your space, your points into two parts. It may, usually it will not split them equally. Okay. Because this is done randomly. The space will also be split randomly. The points will also get split randomly into two halves. Okay. So your root node had all the data points. Now the two children of the root node will have, one of them will have all the points in this yellow region, and the second node will have all the points in this blue region. Okay. Now you take this yellow region, you repeat the same process. Basically, you pick 2 points, you randomly, you build a hyperplane, and that hyperplane splits the region into two parts, and all the points falling on one side form one subnode, all the points falling on the other side form the other subnode. Okay. You do that with all these nodes. You keep repeating it until your node has very few data points. What is the meaning of very few? It's a hyperparameter. It can be decided when you're building the actual search engine. Okay. So it's a hyperparameter. Basically, it's decided by the user. So you keep doing this process iteratively, that the binary tree keeps going deep until all the leaf nodes have points which are equal to a threshold. Okay. So that is the process of building a random tree, one random tree. Okay. So what Annoy tells is build many more trees like this. It's not just building one tree. You have to build many more trees like this. Now, what is the ideology? What is the hypothesis behind this building these trees, multiple trees randomly? The hypothesis is that if there are 2 points which in this data set, if there are 2 points which are close to each other, then there will be at least one tree in which these 2 points will lie in the same leaf node. Okay, that is the hypothesis. Okay, so the hypothesis, again I'll repeat it, that if there are 2 points which are very close to each other, then it is likely that there will be at least one tree in which these 2 points will lie in the same leaf node. That is the hypothesis. Okay. And once you build all these multiple random trees, your search index is built. Now, how do you do similarity search? When a query vector comes, you take the first tree, you go from the root to the leaf node. You traverse, you take the first hyperplane and see whether the point lies on the green side or on the blue side. If it lies on the green side, you go to that particular node and again see whether the point lies on the green side or on the orange side. You traverse the tree from the leaf, from the root to the leaf. Okay. Finally, when you reach the leaf will contain few data points. So you compute the distance between your query point and all the point in the leaf node. Okay. Now you go to the next tree, you do the same thing. You go from the root to the leaf node. Whatever points are there in the leaf node, you compute the distance between the query vector and the points in that leaf node. Okay. So you repeat that, you do it for all the trees. And finally, you merge all these results and find those points which are closest to the query point. Okay. So this algorithm, actually, it's quite a powerful technique. This algorithm is used in the Spotify app. Okay. Spotify app has around 80. Okay. And their recommender system uses a search index which is built using the Annoy algorithm. Okay. And it works quite well. So scaling of these particular algorithm, it scales at least up to close to 100 million data point, it scales well. But as you keep adding more and more points, what you'll observe is you'll have to build more and more trees. Okay, and that will be the challenge. And if you have to build more and more trees, at runtime, you'll have to do a lot of, at query time, you'll have to do a lot of computation. Okay, so that will be a challenge, but at least up to 90 million points, it seems to work quite well. Okay, so another good aspect about this algorithm is building the index, that is building the random trees, can happen parallelly. Also, at the query time, when we are navigating from root to the leaf and then computing the distance, all this can happen parallelly across trees. Okay, if we have 20 different trees and if we have 20 cores in our server, we can traverse all these trees parallelly and come or do all the computations parallel. Okay, so that is another good aspect about this algorithm. It is simple, computationally efficient, scales well up to at least up to 90 million data points, it scales well. Okay, beyond that, if you want to go like in the range of 1 billion or so, there I have my doubts. So the third approach is based on the graph data structure. The third approach is based on the graph data structure. As I've said, we can consider all these vectors as points in n-dimensional space. And if these are points in n-dimensional space, we can consider them as nodes in a graph. Okay, every point acts like a node in a graph. We can connect these points by edges. Okay, so there is this navigable small world graphs algorithm which describes how to build a graph for vectors. Here the idea is we want to connect points which are close to each other. Okay, so every point will be connected to m points which are closer to it. Okay, so here when we want to draw edges from this point, we will see which points are closest to this. We select m closest points and draw an edge from this point to all those other points. So this graph construction, actually, it's a tricky algorithm. It's not that straightforward, but eventually once the graph is built and we have a query vector also. Okay, query vector is also a point in the n-dimensional space. So someone is asking some questions. Just let me finish, and we'll have some time. I'll take up all your questions at that point. So there will be an entry point in the graph. There will be one node which acts like an entry point. And when we get a query vector, we start from the entry point. We see what are all the vectors which are in the neighborhood of this. I mean, we see all the edges of this point. Which edge is closest to the query point? We traverse in that direction. Okay. And then from here again, we see what are all the points, what are all the edges of this particular point. And we compute the distance between the query point and the edges of this point. Okay. So eventually we keep traveling from the entry point in the direction which minimizes the distance between the query point and the nodes. Okay. So this is a graph based approach. It had challenges in terms of scaling. One thing is, when you are traversing the graph, that is at a query time, you are doing sequential operations. Okay, you start at this point. Every time you're doing basically a greedy traversal, right? So you are going from one edge to one node to another node to another node. It's a sequential operation, so you don't have much opportunity to parallel computation over here. So the second thing is, if the number of data points increases, if it goes in millions, then the size of this graph increases, the time it takes to travel from the entry point to the destination point, it can also increase. Also, because of the complexity of the graph, we may not end up at the right spot. Okay. So there are that kind of challenges with latency as well as with recall. And there was an improvement done to this algorithm, which is hierarchical navigable small world graphs, also called HNSW. This is a fantastic technique. Okay, so they have, the idea over here is, instead of building one graph, why not build multiple graphs in layers? Okay, the topmost graph has very few points. The next graph has slightly more number of points. The next graph has slightly more number of points, and so on. So every point that is there in the top graph is also there in the next graph. The points that are there in the next graph will be there in the graph below it, and so on. So the bottommost layer contains all the points. The topmost layer contains only those points which are like very far from each other and very few points. So if you have to understand it, this hierarchical graph system, think of it as a multimodal transport system. Okay. So if you want to travel from New York to some town near Mysore, okay, how would you do that? So initially, you will take long distance flights, right? You will take a flight from New York to London and from London to New Delhi. So that is like a very long distance travel, and that is like navigating the top level graph. Okay, you start off from the starting point, which is, let's say, New York, and you go to London and then you go to New Delhi. Okay, once you reach New Delhi, you change the mode of transport. That means you change from international flight to a domestic flight. In terms of graphs, what it means is you're going from a higher level graph to a lower level graph. Okay. Once you reach New Delhi, you have taken a domestic flight from Delhi to Bangalore. Okay. So that is equivalent to traveling the second level graph over here. Okay. Maybe that is not a direct flight. Maybe that flight goes from Delhi to Jaipur, Jaipur to Hyderabad, and from Hyderabad to Bangalore. So within the layer 2 graph also, once you started from Delhi in the second level graph, you go from Delhi to Jaipur, Jaipur to Hyderabad, and Hyderabad to Bangalore. Okay. So once you have reached Bangalore, you again change your mode of transport. Okay. So that is like when I say changing the mode of transport in terms of graphs, it means you're going from a higher level graph to a lower level graph. Okay. So in this lower level graph, again you start from Bangalore. Okay. You have stopped at Bangalore in the higher level graph. So you start at Bangalore in the lower level graph. Okay. Maybe in the lower level graph, you take a train to travel to Mysore. Okay. That train will also not be a direct train. It will have hops. So you will traverse this graph. In this next level graph, you will again traverse from Bangalore to some other stations, and finally you'll reach Mysore. Okay. Again, Mysore may not be your ultimate destination. Your ultimate destination is a town near to Mysore. So again, what you'll do, you'll change the means of your transport. You'll go from rail to roadways. Okay. When you do that, what it transpires is again you're changing the graph. You're going from a higher level graph to a lower level graph now. So you start at by road. So that is the mm, philosophy behind hierarchical navigable small world graphs. Here you have multiple layers. The long distance travels, they all happen in the topmost graph. The topmost graph has very few points, so the large distance travels happen very quickly. The next level graph has slightly more points. So what you're trying to do is, as you're going from the top level to the bottom level, one thing is you're traveling lesser and lesser distance. You have traveled bulk of the distance in the top level graph. You're traveling lesser distance in the next level graph. You're traveling lesser distance in the next level graph. But at the same time, you're zooming in to that region where your query point is. Okay. So this is a very, very powerful technique. It's really fast. It can scale very well. I mean, I've tried it myself. It scales easily up to 100 million points. Up to 10 million points, it is super fast. I mean, it gives you the results in like 6 to 8 milliseconds. Okay. But as you add more and more points, let's say if you have added 100 million points, then it might take some time, 100 milliseconds, 150 milliseconds, that sort. But still, it is relatively quite fast. And it gives very good recall also. Okay. But the challenge over here is graph is a bulky data structure. Okay. Storing the graph when the number of points is huge requires a lot of memory. That is one downside of this approach. So, okay, we are short of time. I'll try to give you the pointers. So other than these three techniques, there are other hashing based approaches. Locality sensitive hashing is another popular algorithm which has been used for text similarity search and also in many other applications. This book, Mining of Massive Data Sets, it describes this algorithm very well. Okay, it's a freely available book by David Ullman. Anyone interested can look at that. And then there are certain hybrid approaches. One popular hybrid approach is doing quantization. Quantization is the process of compressing the data. Okay, so let's say you have 700 dimensions vector. All of them are floating point values. So what quantization does is it compresses your data into maybe 70 integer values or 70 binary values, something like that. Okay. And once your data is compressed into like 10% of its original size, then the amount of computation you can do is much more. Okay. So quantization, essentially it's a compression technique, but you once you have compressed your data, you can apply quantization with clustering, quantization with any other algorithms. Okay. The downside of doing quantization is that it you are losing information. Once you are doing compression, you are losing information. Once you are losing information, it will have a serious impact on the recall. Okay. So if your application has a decent recall requirement, then you should not go for quantization. But if the recall is not such a big issue, you have large volume of data, you want to give results quickly, and you want to consume very little space, then quantization is a very good technique in such a scenario. The last thing I want to mention is there is another hybrid approach which uses both clustering and graphs. This is a paper, SPNN, highly efficient billion scale approximate nearest neighbor search, by Microsoft guys. This technique is a very, very powerful way of combining clustering and graphs. It scales up to like even a billion data points and gives you results in no time. Okay, if you read the paper, you'll see that even at a billion scale, it gives you the results in few milliseconds and at a very high recall, above 90. Okay, so this is one of the latest papers. When it comes to open source tools, NOI algorithm that we have seen, it has its own open source repository. If you want to try NOI, the entire code base is available online on GitHub. You can try that. But what I would suggest is take a look at the Facebook AI Similarity Search library, FAISS. It is also open source library, has fantastic GPU support, supports a wide range of algorithms, exact search, clustering based, graph based, hashing, quantization. It supports almost all of them, okay, except maybe for the tree part of it. It has a lot of support. It is very efficient library, has GPU support as well. So if you want to start somewhere, this would be a very good starting point. Now here are the two very good resources. First is the ANN benchmarks GitHub repository. This repository not just provides you with data sets, it also provides you with links to many other open source implementations of like around 20 to 30 algorithms, okay, are available open source, and it has links to all of them. And also they have benchmarked all of these algorithms on variety of data sets. So you can take a look at that as well. And then finally, this big ANN benchmarks data set gives you like 5 or 6 data sets, which are very large, like up to 1 billion data points. And they are all freely available on this website. Okay, so finally, to do a quick recap, this is the big picture which you have to take back. Okay, whenever you are building applications on unstructured data, the two key things which will come into the scene is, one is the AI model that you need to use to convert the unstructured data into vectors, and second is vector database, which vector database you have to choose to store and retrieve the data. Okay, and this big picture fits into like many applications, either fully or partially. Okay, so if you have to take back anything, this is the thing. Thank you very much for your time, and now we can take up questions.
Thank you, Mr. Ji. I think there are a couple of questions from learners. This is from Sri Patipai. Is multimodal search using vector databases possible using multiple types of input data?
So, see, we are not feeding raw data into the vector database. Vector databases understand only vectors. So as far as the vectors are of the same dimension, okay, you can feed any kind of vectors. Those vectors may actually represent text, those vectors may represent images, doesn't matter. Okay, so if you go back to this picture here, the multimodal aspect comes into the AI model part of it. Okay, there are some AI models which accept text, images, audio, everything, and the single model will convert any kind of data into vectors. Okay, once you have a vector, the vector database only understands the vector part of it. So yeah, in that sense, you can feed the multimodal data into a vector database.
Yeah, one more question from the same person. How do we evaluate or quantify the effectiveness of the results of the vector databases, which might sometimes be subjective in nature based on the user's subjective experience while using the vector basis?
See, the subjective part, I'm not too sure about that, but there are objective ways of evaluating the efficiency of vector databases. In terms of subjective is always, it is application dependent, right? We cannot make a generic comment on the subjective part of it. But as far as evaluating the vector databases is concerned, you can evaluate them in terms of how much volume they can ingest, what latency they provide, what is the accuracy or recall. There is one more thing, the throughput. Okay. Uh, Throughput depends on not just the algorithm but also the infrastructure, but still throughput, algorithm plays a role in throughput. And in terms of the infrastructure requirement and the cost, these are the ways in which we can evaluate a vector database. Anything else, Prakash?
That's it, Visajit. Thank you, Visajit. Now we have Aishwarya Pathak, who is from TimesPro. Over to you, Aishwarya Pathak.
Thank you so much, Prakash, and thank you so much, Vishwadip, for such an amazing session.
Thank you.
So, I am here to talk a little about a new program that we have launched with IIT Delhi. I wanted to inform our attendees about that since we have this program going on AI. So, after successful completion of our first batch, we have launched a second batch of IIT Delhi Artificial Intelligence and Machine Learning for Industry program with IIT Delhi. So this program is a beautiful blend between theory and practical, with foundation topics like practical Python to an advanced topic of deep learning. We will be covering tools like TensorFlow, Pandas, NumPy, and more. And not only this, with contemporary case studies and practice sessions, the program aims at providing hands-on experience in applying advanced AI and machine learning techniques that are used by leading tech and non-tech companies. For example, Google, Coca-Cola, Amazon, and the list goes on. To provide our learners with a good experience, we will be having esteemed faculty from IIT Delhi who will be teaching the course, and there will be international guest lectures from the industry experts. So, fresh graduates who are seeking a career in AI domain, or professionals who are looking to gain AI expertise, and those professionals who are looking to upskill themselves in AI, data science, and machine learning, this program is the answer. So the program will also create an opportunity of interacting with the faculty and networking with the peers with one-day optional campus immersion. And on completion of the programs, the learners will also receive an e-certificate from CEP IIT Delhi, proving your experience and expertise in this field. So I will drop the program link in the chat box, Prakash. I would request you to share it with the attendees, and do check the program out and unravel the AI enigma with TimesPro. Over to you, Prakash.
Yeah, thank you, Aishwarya. Adding to this, this is one of the successful program which is run by IIT Delhi along with in partnership with TimesPro, and we have almost 98% of NPS for this program, which is very successful. So I request all the learners just have a look, and if you feel that it is aligned to whatever you are pursuing or looking for, please have a look at this program. And coming to apart from that, we have one AI community on Discord channel where multiple learners who are interested in AI and everything are there. So you can join the Discord and you can view the resource files which are available for free, and you can have peer-to-peer learning as well. So thank you everyone. Thank you for your time and all the best for your future.
Thank you.
Yeah, thank you, Vishwajit.
Thank you.